Hi, this is Dan Abbott. I'm making this video to show my print reading class what those 6 objects look like on the handout that you're going to use to pick 2 of them and draw them and add dimensions to. What you're looking at is a split screen. On the left is SolidWorks, and I've got the model itself. On the right is the drawing that came from the Gesicki, venerable old drafting textbook, and I love the illustrations because they're done by hand. They do force you to do a little interpreting. And I do want to point out some things that you cannot do on your drawings, which is right here where it says C-bore from bottom. That stands for counterbore. That's an abbreviation, but I want you to use instead the symbols, which are shown above here. And what that means, and that's the thing that you're probably least likely to be familiar with, what that means is there's a hole that goes through this that has a diameter of 440 thousandths of an inch, 0.44. There's a counterbore. The counterbore is a little pocket. I'll show you in a second what that looks like. And the counterbore has a diameter that's larger, which it has to be. And the depth of that counterbore is 0.5, but it doesn't start at the top of this hole, it's from the bottom. So if we look over here, we're talking about that hole right here. If I bring it up, there's your counterbore. Counterbore is a pocket. The depth of the pocket's the distance from that surface to this surface. That's 0.5 inches because it tells me that right there with that depth symbol. The diameter of that hole is 0.62. The diameter of that hole is 0.44. Now that's what it looks like isometrically. That hole, the big hole, goes all the way through. You can see that. That slit goes all the way through. Something's going to be bolted on here and that'll be clamped to something. Otherwise it's a fairly straightforward shape. I'll just rotate it around so you can see it from all sides. I'm purposely not rotating it into the traditional orthographic position because I want you to do that yourself. But there's what it looks like from the bottom. Looks like from the other side. You can see that hole going down through. And then the counterbore on the bottom. That's what it looks like. A couple other things here. On places where you have 2 numbers, right here you have 1.125, 1.124. That's a specific tolerance, and tolerance means the size of that hole must fall between those 2 numbers in order for this part to work. You can tolerate that much variation without changing the function of the part. The other dimensions have 2 decimal places, and their precision would be placed in the title block, and it would be based on how many decimal places they have in the United States. That's not something that can be used in other countries. The ASME standard permits tolerance information to be carried by the precision of the dimensions placed. Metric drawings in the ISO, the International Standards Organization, do not. So that's this one. Now let's look at the hinge block. A hinge block has a number of dimensions as well that are tolerance dimensions. There's also another counterbore here, 10 millimeter hole. Counterbore is 14 millimeters. There should be a diameter symbol here. I took these from one of the Gesicki textbooks, and these were edited after the fact. Mr. Gesicki drew most of these probably close to 80 years ago. At any rate, someone just left out the diameter symbol that would normally go right there. You have a few other abbreviations. Cold rolled steel is what CRS stands for. And then you don't really need to worry about this for the drawing itself. You're going to draw this with multiple views and then put the dimensions on it. And when you do sketch this, you can just sketch it because you're going to be doing this as sketching. Just sketch those sizes somewhere close to whatever that tolerance dimension is. If you're using AutoCAD, and some of you might be using AutoCAD, then you're going to do what's called max material condition. You're going to take, in a situation like this where you're creating a void, you're going to take the smaller of the 2 numbers. Down here where there's a hole also creates a void, smaller of the 2 numbers. Any place that actually has material associated with it. And there are no dimensions like that here. So in each of these cases you'd use the smaller of the 2 numbers. I also want to point out that in SolidWorks, any place where there's a tangent edge, where that surface meets this surface through a tangency, because it's a computer and it sees that as a surface and that as a surface, it always puts a line between them. But in fact, with the eye, we would not see that line. It would look more like this. Now there's your counterbore right here. If I tilt it up, you can see that that opening right there represents the larger of the 2 numbers, diameter of 14. That surface right here would be the smaller 10, and the depth from that surface to this surface, well, probably makes more sense to call it from that surface to this surface, because it would have to go from that flat surface. That depth is going to be 8, and the depth in this case is given as a minimal depth. So the fact that it's deeper over here because that arc starts to go up, doesn't matter. You're still going to measure it from that end right there. The bottom shows you the holes go all the way through. Got a couple holes in the side as well. Now that little cutout is represented over here with that hidden line. That little cutout is just a relief. I'm not sure exactly what it would be for on this particular part, but it's there, and the radius of that is given right there as a radius of 16. The radius of the big arc is a radius of 41. That's the radius of this right there. Now I'm going to go back to showing the edges, just a little easier to see what we're talking about here. So I'm going to rotate this around like I did the other one, so that you can see what it looks like, and of course you can stop this video and go back and forth. The reason I'm doing this is I want you to be able to visualize this and then determine how to best represent it orthographically by doing the sketching. Go this way, and it looks like that. Isometrically, looks like that. More or less like this. These are both isometric drawings. It's not exactly the same angle on this, but you can see how it's portrayed. A little difficult in isometric drawing sometimes to understand what's going on. For instance, right here there's a hole. It doesn't tell you it goes through the part directly, but it does go through the part, and the way it does tell you that is by not giving it depth down here. So that diameter of 6, when applied to a hole, indicates that it goes all the way through the part, because if it didn't, you'd have to indicate a depth. Counterbore we just looked at. Everything else I think is pretty clear. We're going to move on to the next one. And before we go on to the next one, I did not tell you what FAO stands for, and that's something you don't see on prints very often anymore. It stands for Finish All Over, and it implies that it might be possible to think you didn't have to machine this to make everything smooth, when in fact it has to all be machined. So that either was a forging or a casting, probably a forging, that must now be machined in order to achieve the dimensions given. Now we'll change to the next one. The next piece we're going to look at is called a vibrator arm. You can see that it was drawn isometrically a little differently than this one. We could kind of put it in that position if we wanted to. This has another feature that we haven't seen yet, which is a chamfer, although it doesn't have the whole word here, C-H-A-M-F-E-R. The chamfer is going to be a dimension by an angle. And if we take a look at this model over here, the dimension given is the distance from this face down to that edge right there. So that distance would be like we're drawing a right triangle in here. We draw the right triangle, the distance from here is going to be 0.25, and the distance from here back is going to be 0.25. And that means I'm drawing this on the surface, but the fact is that's the part that gets taken away. So if we look at it from the top, so what it's saying is the distance from here straight across to line up with that is 0.25, and the distance from that point right there, so it lines up with this, is also 0.25, and that angle is 45 degrees. That's the part that gets cut off a little bit. That's a very common way to dimension a chamfer, because a 45-degree chamfer has legs that are the same length on either side. Otherwise, you've got another counterbore here. That counterbore is here, with a little pocket in the top. It goes down a certain depth, half an inch in this case, 750 thou. By the way, and that's how machinists would identify a dimension like this. In a machine shop, the unit of measurement used in the imperial system, in the U.S. system, is a thousandth of an inch. In metric shops, it would be 100th of a millimeter. So that would be called 750 thou by a lot of machinists, and that means 750 thousandths of an inch. You wouldn't call it 7500ths, and you wouldn't call it 50 hundredths. It'd be 500 thou and 750 thou. So we'll take a look. This is fairly straightforward. I think there is a slot on the bottom that you see right there. They only show you the hidden lines part way, just to simplify the asymmetric drawing, but it does in fact go all the way through. So let's rotate that around for you. And again, I'm purposely doing this so it doesn't give you the standard orthographic views, because I want you to think of what those would be and then identify them in your mind's eye. And once again, the software is showing us these tangent edges. You would not see those with the naked eye, so your drawing would be of a part that looks like that. Nothing else. CHAM, again, chamfer is an abbreviation for chamfer. You don't need to put that in. When you identify a feature like that by pointing at it and giving a dimension, in this case there's spaces on either side of the X, but when you give a dimension 0.25 space X space 45 degrees, that is a chamfer. There's no reason to identify it in addition with a term. All right, I have another one. This is called a counter-bearing bracket. Bracket would hold something, and something would be bearing, and there'd probably be a shaft in it. It might have a sleeve or a plain bearing or a bushing of some kind. This is what it looks like over here, although because there are so many tangencies, there's a lot of lines here that would not show up in the drawing. So in fact the part looks like this. Now this introduces a couple of other mechanical elements, and that is what are called fillets and rounds. And you indicated that the size of fillets and rounds, if they're all the same, and they normally are in a cast part, as a radius of 3. This is all metric, of course. Rounds are any edge on the outside. There's a round right there, because it's a arc that's tangent to two surfaces on the outside. Down here we have a fillet. A fillet is the same thing geometrically, but it's on the inside. When you have a fillet or a round, it's always tangent to the surfaces that it connects. And the purpose of that, and when I said this is a cast part, you can tell it's a cast part because this little poching, which are little speckles that are there. That was the way when we drew by hand and drew isometric drawings. That's the way we used to indicate that something had a rough surface from being cast. Cast parts are normally cast iron, which is what this is. That's what CI stands for. And cast iron is normally cast in molds that are made out of sand. Because of that, the sand imparts a texture to the surface. It also has a certain hardness at the surface because it cools so fast there. So that from a point of view of making a usable part, you might start with a cast part, but then the key features have to be machined. In other words, somebody had to cut away that face, bore that hole out, and how did I do the back? And also, and the back had to be machined as well. That's what gives it that square edge. And I don't know that I knew that for sure, but just looking at it, it appears to be that the back would be machined as well. The bottom has to be machined because the bottom has a piece that's going to slide down into a slot. So this is all flat, that's all flat. And what that means is you're going to have corners instead of surfaces that are curved. So these bottom edges are sharp corners, sharp corner, sharp corner. Whereas the places representing surfaces that are still in their cast form still have the fillets and rounds, so they've got the smooth transition. Unusual to have a hole just drilled down through like that without having a spot face around it, but that's how this is drawn, so that's how I want you to go ahead and create it. That's called a rib, and that rib is in there just to support that and give it additional support. And that's probably all you need to know about this part. There are, again, 2x, no space, looks a little like a space, but 2x with no space, then a space. The diameter means that both of those holes are the same size. Now we have the feed rod bearing, or as a student once described it, the monkey face part with the Google eyes. This part's similar as far as the shape goes. A lot of tangencies, one up here, there's one over here, right there. There's also smooth fillets and rounds, and those all have a radius of 3 as well. When you're sketching this, by the way, the sketch paper that I gave you has blocks laid out for inches, but they're decimal inches, so there's 5 little blocks per inch, which means you can use this as a way of sketching with metric if each one of those little blocks, which is 0.2 inches, can be sketched as 5 millimeters. Nothing different about this in particular. Again, parts of these, this is a raised boss. That right there. that raised boss has got a purpose, and that's what I was saying I thought was missing from the other one, or a spot face. The purpose of that is to strengthen the part right there, because cast iron is very brittle. And when you bolt cast iron down by putting bolts down through it and then tightening it down, which is what you would do here, it's helpful to have a little bit of a thicker place where the bolt is actually putting its pressure. You also need to have a flat surface, because if you bolt something that's cast iron with that rough surface, all those little teeny bumps tend to concentrate stress, and the stress concentration has a tendency to crack the cast iron. So in this case, the purpose of that raised boss is really to put that flat spot there so that you can put a bolt in it, probably with a washer, so that the surface itself distributes the forces and doesn't concentrate them. And it also thickens the part that's being held down, so it strengthens it a little bit. And did I? Yeah. Let's say it looks like that's an edge right there. You know what? I never put a fillet on that edge. I'm going to do that right now. And whoop, I don't want it to be quite that big, that's for sure. Well, let me do it a little differently. This is SolidWorks. This has nothing to do, folks, with what you're doing with your sketching. I just want to go and add in that fillet right there. Oh, I see how I didn't put it in. It didn't like it. All right. Well, you don't need to see this whole thing. I am going to fillet it, though. And I'm going to do that individually by saying put a fillet on that edge right there and give it a size of, is this in inches? No, 3 millimeters. Alright. So that's what it would look like. It would be filleted on all sides. Now we'll take a look at the next one. So now we're at the last one, which is something they're calling a lever hub. This is also done in metric, obviously. There's nothing about this that we haven't already looked at. So I'm just going to let you go ahead and draw it. I will let you see what it looks like over here. The thing that's unusual about this is that I would have expected this to be a cast part, given its shape, and I would have expected radiuses here representing those fillets. But draw it the way it's shown there. So what this is going to look like is this. The bottom is flat. A couple holes go through. You got the corner cut off right there. That's a chamfer. Someplace it should tell you what that chamfer is. What it does here is it, instead of calling it out as a chamfer, it just gives you the angle of 45 and the distance back of 12. And that's all you're going to have to do there is draw that in such a way that it goes back 12 millimeters or so. It's a sketch, so you're just coming close. Just make sure that everything you do is orthographically correct, your line weights are correct, your line types are correct, and that you leave enough space between all the views so you can put the dimensions in later on. Yeah, so that's what it looks like moving it around like that. That's what it looks like moving it around like this. I think that's probably enough. Looks like that. I can't remember if I actually turned around the last one we did or not. Let me go pause this for a moment, bring it back, and then do that in case I did not show it to you by. Yeah, I am back. I don't think I did, so let's just see what that looks like. Flat on the back, holes go straight through. The only variation from straight holes is those raised bosses right there. Put the edges back in just so you can see a little better. Then everything is rounded where all the intersections take place. Looks like this. And it looks like that. Alright. That's enough for this. I just want to make sure you have something you can refer to while you're doing those orthographic sketches. These, you're going to be very careful on these, take into account all the comments that I made on your last assignment. Make sure that you line things up. Make sure that you understand the fundamentals of orthographic projection. Make sure that any feature that shows up in one view is projected correctly to another view. Use a miter line if you think it would be helpful to go from the right side view to the top view. Use third angle projection, not first angle projection. Do not label the views. People know what a front view is, they know what a right side view is, they know what a top view is. I think that's enough.